Hi, in this video, we want to take a look at testing subsets of our coefficients from linear regression to see if that subset, all of the coefficients are equal to 0. Okay, so normal hypothesis testing that most people are more familiar with, we take a look and see if one particular coefficient is equal to 0. Here, we want to look at, one or more. Okay, so if I look here, the first hypothesis that we can look at, now this is scalar beta. This is one entry for beta. When things are written down, sometimes it's a vector, sometimes it's scalar. Unfortunately, it's hard to keep track of which one's which. This hypothesis testing is that individual coefficient is equal to 0, or the individual coefficient is not equal to 0. That's our first goal, try to understand that. And then we want to expand this. We want to be able to say, is this collection of coefficients all equal to 0, or are we in a situation where one or more are not equal to 0? Now, you'll notice I've got subscripts here. So, the subscripts, a subsequence is to denote which ones, the first one, second one that we're interested in for hypothesis testing. To make all the mathematics easier, what we're going to do, we're going to say that when I'm doing hypothesis testing, all of the earlier index coefficients are not in the hypothesis test, and all the later index coefficients are in the hypothesis test. So what we're going to do, we're kind of like looking at two models. One where we have all of the coefficients, that's going to be corresponding to our alternative hypothesis, and then we'll have the null hypothesis is where all of the later ones that we are testing on are equal to 0, and the first ones are kept, and that will be like a reduced model. All right, so as I work through, I'm saying that all of the later betas in the beta vector are being tested as being equal to 0, and all the earlier ones are not under question whatsoever. So we're going to go ahead and take our X matrix, our predictor variable, or predictor data, and we're going to break it up into two submatrices. The X1 corresponds to the coefficients that we're not testing on, and the X2 corresponds to all of the variables that we are testing the coefficient on. All right, and so we can take our, our well understood formula, and we can write it this way. So here I have X1, X2. Here are the ones that are above reproach for the coefficients, and here are the ones that we are testing on. And remember, our test is that all of the entries of this subvector are equal to 0, or one or more is not equal to 0. So we're taking the point of view that either all of them are 0 or not. So our hypothesis test is that beta 2, that's a vector, is equal to the 0 vector, or beta 2 vector is not equal to the 0 vector. All right, so if we fail to reject the null hypothesis, then we're going to want a reduced model. Okay, well, for a reduced model, of course, it will be something like this. Now, the star denotes that I'm dealing with a different situation. So this is the star corresponds to the reduced model, not the full. So remember, if my data predictors are not orthogonal to each other, then removing predictors will change the coefficients on the ones that are kept in. All right, so because of that change, we have to put a star there. Now, if X1 and X2 are orthogonal, the beta 1 will not change whether we're doing reduced or full model whatsoever. All right, well, so if this is my model, this will be my estimate of the coefficients. I know it's surprising. So this is reduced model coefficients, and here is the full model coefficients. And so here, remember, if X1 and X2 are not orthogonal to each other, this beta 1 hat star is different from this beta 1 hat. Okay, well, let's go ahead and take a look at sum of squares total. So sum of squares total is the sum of the squared deviation of y from the sample average of y. Well, let's go ahead and let's write that in terms of vectors and matrices. So I'm going to go ahead and rewrite this as y transpose y minus n y bar squared. Okay, familiar formula. So now what I'm going to do, I'm going to add and subtract terms in there so that I can rearrange this into something that is a little bit easier to interpret. So I'm going to take the regular full model estimate part here. So beta hat transpose X transpose Y. And I'm going to add and subtract the same thing. And then I'm going to do the same thing, but with the reduced model. So I've got X1 and a beta hat star 1. Add and subtract. And so I add and subtract the same thing. It's the equivalent of adding 0 does nothing. Add and subtract the same thing, same as adding 0 does nothing. All right, so this is the same as my sum of squares total. Okay, well now I'm going to put parentheses around things to group them together. So I put a parenthesis around these two, boom, put parenthesis around these two, boom, put parenthesis around these two, boom. Now, let's take a moment and look at what we have. All right, well this will correspond to like modeled value, and then over here, this is observed value, right? If I factor out this y, I see that I've got y transpose minus beta hat transpose X transpose, but factor out the y. And we look at this for a moment and we realize that this is equivalent to the sum of squares total for the full model. Okay. Now, if I look over here, I can interpret this as the sum of squares regression for the reduced model. So if I was to change this, so this was just beta hat and X, then this would be my sum of squares regression, if we remember that formula. All right, so sum of squares regression for the reduced model, boom. Now here, what we're gonna do is, if I look at this, I notice, you know, I got the right dimensions, I can do the subtraction, everything's good there. If I factor out the y's, I can interpret this as a sum of squares sum of squares based off of beta 2 given beta 1. Okay. And so if we think about it for a little bit, remember that sum of squares total equals sum of squares error plus sum of squares regression, right? So the total variance is equal to the variance that, or the sum of squares total is equal to the sum of squares from the error plus the sum of squares from regression. Okay, so sum of squares beta 2 given beta 1 is equal to sum of squares regression full minus sum of squares regression minus reduced. If we look at this for a little bit, we rearrange these terms. All right, so if the null hypothesis that beta 2 is correct, if beta 2 equals 0 is correct, we expect sum of squares regression full to be close to sum of squares regression reduced. All right, so basically we're saying that adding the additional predictor variables does not improve the model by much. That's really what this is saying. If beta 2 is actually equal to the 0 vector, then my sum of squares regression full is not going to be much bigger than sum of squares regression reduced. There will be a difference. No matter how you cut it, then there will be, or not necessarily an improvement, but you can bank on it, that in real data, that the sum of squares regression will be larger, sum of squares regression full will be larger than the sum of squares regression reduced, but if I'm in this situation, they're going to be close to each other. All right, so if they're close to each other, then this is going to be a pretty small value. If this is a small value, then my sum of squares beta 2 given beta 1 will be close to 0. And it's a sum of squares, so it has to be positive. If it's close to 0, that's as small as I can get it. Now, if the null hypothesis, or sorry, if the null, so this should be A. If the alternative hypothesis that's not equal to 0 is correct, we expect that the sum of squares beta 2 given beta 1 will be larger. All right, so this is kind of a critical component of our thought process for this. All right, so now let's do a little bit of side work for something that's going to help us out. All right, so we have Y transpose, a matrix, and Y on the right, so it's a quadratic form, and this is I minus 1 over Nj. Hopefully this is familiar to us by this point. All right, well, what I can do, I can go through, I can distribute the Y's to get this, And now what I'm going to do, I'm going to add and subtract terms to what's going on. So I'm going to take this term here. So you notice that this looks a lot like the hat matrix, maybe? All right. So I add this term, or I subtract this term, and I add it. I subtract this term, and I add it. Okay. So I've got these 4 terms here are the equivalent of adding 0. Adding 0 does nothing. Okay. So now what I'm going to do, I'm going to take these 2. I'm going to factor out the y's. I'm going to take these 2. I'm going to factor out the y's. I'm going to take these 2, and I'm going to factor out the y's. Hopefully you feel a pattern going on here. All right, so this is from the first 2 together. Boom. This is from the second 2. So this and that. So, and then next we get these 2 together to give me that after I factor out the y's. All right, so now what I'm going to do is I look at this and I realize that this is the hat matrix for the full model, hat matrix for the full model, hat matrix for the reduced model, hat matrix for the reduced model, and then 1 over n times j. Okay, so now I get this. Now remember, H is idempotent. So the hat matrix is always idempotent, and 1 minus H is idempotent, and the rank of 1 minus H is going to be equal to n minus k minus 1. So remember, with an idempotent matrix, the eigenvalues are always 0 or 1, and the number of non-zero eigenvalues is going to be the rank every single time. And idempotent, by its definition, implies that square. All right, so if I think about this for a moment, really, the reduced hat matrix will have all of these same properties because it's derived in the same manner. I'm just using fewer predictor variables to derive it. So we know that all of the idempotent properties of H, the rank properties, everything that we get for free for H, we can apply to the reduced hat matrix. All right, so H minus H2 is going to be idempotent with rank H. H is equal to the length of beta 2. Now, something about this is that in everything that we're doing, we're assuming that we have full rank and we have more observations than we have predictors. And when I say predictors, that includes the y-intercept. But wait, there's more. H minus H2 is going to be equal to this, which, you know, that's obvious. All right, so now let's work through this. First, let's do a little bit of side work. What's H times X? Well, that's H, right? And that's X. Well, if I look at this, I notice I have, you know, a parenthesis to an inverse, and I have exactly what's on the inside of that parenthesis. So if I rewrite this, I know that that's going to be equal to X. All right, so H times X is equal to X. All right. So this tells me that X is also equal to all of this stuff. Okay, okay. So I know that this has to be true. This equation, X is equal to this stuff times X. Now, let's go ahead and apply this to X1, X2. All right, so when I do this, I get X1, X2 is times the hat matrix with X1, X2. All right, now let's go ahead and distribute X1, X2. I see X1 is equal to this, X2 is equal to this. All right, the only way that this can work out, if I think about the dimensions in the entry positions of this matrix multiplication, is that X1 has to equal all of the full hat matrix times X1. X2 has to equal the full hat matrix times X2. Okay. So X1 is equal to the full hat matrix times X1, and X2 is equal to the full hat matrix times X2. Okay. So now, let's consider H times reduced H. All right, well, let's just write it out. Well, I notice that this is H times X1, right? Well, that's just X1, so that has to be reduced X, reduced H. Boom. Things are just flowing, flowing, flowing. All right, now let's do exactly the same thing, but this time, let's switch the order of multiplication. So here, I've got reduced hat times the full hat. now I realize that the hat matrix by its construction is going to be symmetric. So I have x reduced x times full h, and I'm putting transpose. Well, remember, if I take the transpose, I put a parenthesis around it, I switch the order. Boom, I get this, h times x1. Well, we just worked something out. This is x1, so that tells me that I have x1 here transpose, and I look at that, and hey, that is the reduced hat matrix. Boom, we got this, we got this. So it doesn't matter which order the multiplication is, h times reduced h is going to be reduced h every single time. Okay, so now, what are we going to do? I want to show idempotency. That means I have to square it. I have to get the original thing back. All that junk we were just doing was all about showing that when I square it, I'm going to get the same thing back. All right, so when I square this and I distribute, I know I'm going to get h squared. I'm going to get h times reduced h. I'm going to get reduced h times h, and I get reduced h squared. Okay, well, we just worked out a moment ago that this is h1. We worked out a moment ago that this is h1, and we know that a hat matrix is idempotent, so therefore this is just h1. Well, boom, we get that. All right, that shows us that h minus reduced h is idempotent, because when I square it, I get the original back. Now, something that's important about this is that this only works out when we're working with the same predictor variables. When my reduced matrix is a subset of the vectors from the full. That's important. All right, so now, next thing. So in that theorem, remember that we also had something about the rank. Well, how am I going to approach the rank? Well, if a matrix is symmetric and idempotent, then the rank is equal to the trace. Okay. Now, the proof of that just comes from singular value decomposition or eigenvalues, however you want to go about it. But if I take the rank of h minus reduced h, all right, well, that from the theorem, we know it's going to be the trace. So why is this equation correct? All right, it's correct because if I'm dealing with a trace, well, sorry, so if I'm dealing with a trace, I can change the order. If I take the eigenvalue decomposition, the Jordan canonical form, I can take the basis vectors and its inverse, put them next to each other, they cancel out. Well, what's left are the eigenvalues, which are 0 or 1, and all the zeros add up to 0. All the ones will add up to the rank. Okay, so here I have the trace, and well, that's addition, right? If it's addition, I can just switch the order. Okay, so now the trace of full hat minus the trace of reduced hat, I can switch the order because on the inside of a trace operation, I can switch things freely, as long as multiplication makes sense. All right, so now I look at this, I realize that's an identity matrix. I realize that this is an identity matrix. All right, well, what are the dimensions? Remember, this is the full version, and this is the reduced version. So the reduced version has fewer columns, fewer rows. All right, so, well, by how much? Well, h, right? So this is going to be a k plus 1 by k plus 1 identity matrix. This is k plus 1 minus h identity matrix. So when I take the trace, I'm just adding up the ones, and we get elementary school arithmetic. Boom. My dog is whining. She wants in, but she's just going to have to wait. I don't know if you can hear her. All right, so now, if y is multivariate normally distributed with expected value that we are familiar with, x times beta, and we have constant variance and independence between observations, so our covariance matrix is sigma squared times I, then we get three things happening. First and foremost, this quadratic form of y transpose x minus hy divided by sigma squared, this is going to be chi-squared distributed with n minus k minus 1 degrees of freedom. Y transpose h minus h1 times y, sigma squared, that quadratic form is equal to, or is distributed chi-squared h degrees of freedom in non-centrality parameter of lambda 1, or lambda 1 is this thing right here. And then furthermore, the numerator of both of these are independent. All right, now how do we prove this? Well, not that long ago, we worked out all of this business. So we know that this is equal to these individual components. Okay, well, what I can do, I can adjust some terms to see, how did I get this? Oh, I move over the 1 over nj portion, I move it over here. Now I look at this, I notice that I have 1 minus h quadratic form, h minus reduced h quadratic form, and I have h reduced h quadratic form. All right. Now they're idempotent, and because of a theorem, we know that the chi-square distributions automatically follow for us so nicely, so beautiful. Now this term is equal to this. So I've got the middle term is, so if I take this, I recognize that I have a hat matrix in the middle, and then I factor out the x sub 2's. So it's like this. I realize I have an idempotency in the middle, so I can, and symmetric, so I can rewrite it in this format. In this format, I can see that this is, in a funny way, the dot product between a vector and itself, which means I have positive definite. Yeah, I'm positive definite as long as I'm not dealing with the stupid case. It's positive semi-definite if I have low rank, but we're not dealing with that. All right, so because of the positive definite aspect, lambda 1, the non-centrality parameter, is equal to 0 if and only if the beta 2's are equal to 0. And so that gives us the rest of it. And that's all I've got for you. Take care and goodbye.